Today we're doing 4.4 coordinate systems. In general, people are more comfortable working with the vector space Rn and its subspaces than other types of vector spaces and subspaces. The goal here is to impose coordinate systems on vector spaces, even if they are not an Rn. Let's look at Theorem 7, the unique representation theorem. Let B, so that is beta, but we call it B, be B1 all the way to Bn, be a basis for a vector space V. Then for each vector x in V, there exists a unique set of scalars C1 to Cn such that x equals C1 times B1 plus all the way to Cn times Bn. B coordinates of x, or also known as coordinates of S relative to the basis B. Suppose B is B1 all the way to Bn is a basis for a vector space V, and x is in V. The coordinates of x relative to the basis B, or the B coordinate of x, are the weights C1 to Cn such that x equals C1 times B1 plus all the way to Cn times Bn. In this case, the vector in Rn, x with the basis B is C1 to N1 is called the coordinate vector of x relative to B, or the B coordinate vector of x. Let's look at example 1. Let B be B1 and B2, where B1 is 3, 1, B2 is 0, 1, and E be E1 and E2, where E1 is 1, 0, and E2 is 0, 1. Suppose that vector x is in R2, has the coordinate vector, the B coordinate vector of x, 2, 3. Find vector x. So the first thing that we're going to talk about is say if the B coordinate vector of x equals 2, 3, then x equals 2 times 3, 1 plus 3 times 0, 1. So x would be 6, 5. This is because x is 2 and 3, and B1 is 3, 1, 0, 1. And then if my E coordinate vector of x equals 6, 5, then x would equal 6 times 1, 0, plus 5 times 0, 1, which would be 6, 5. Those are the same. Therefore, the coordinate vector of x relative to E equals x. If E is the standard basis in Rn. Let's look at a graphical interpretation of the coordinates. So first we have E1 and E2 here, and this would be x. Okay, this is our B graph paper. So we'd have B1 and B2 here, and this would be x, because the B coordinate vector of x is 2, 3. From the last example, 6, 5 equals 3, 1, 0, 1 times 2, 3. These are the weights of I and j, and those are the weights of B1 and B2. For the basis B, we have to let P of B be B1, B2 to Bn, and our coordinate vector, our B coordinate vector of x, BC1 to Cn, then x would be PB times the coordinate the B coordinate vector of x, and we call PB the change of coordinates matrix from B to the standard basis in Rn. Then our B coordinate vector of x equals the inverse of PB times x. And therefore, we're supposed to have a P inverse, let me write that there. P inverse of B is a change of base coordinates matrix from the standard basis in Rn to the basis B. Let's look at example 2. Example 2, let B1 be 3, 1, vector B2 be 0, 1, and B be B1 and B2, and X be 6, 8. Find the change of coordinates matrix P of B from B to the standard basis in R2, and the change of coordinates matrix P inverse of B from the standard basis R2 to B. If X equals 6, 8, then use P inverse of B to find the B coordinate vector of X, 2, 6. So the first thing that we have is PB they give us is B1, B2, which equals 3, 1, 0, 1. So my inverse of this would equal, switch these, well, it'd be 1/3, and you'd switch those and negative the other one. So I would have 1/3, negative 1/3, 0, 1. If vector X equals 6, 8, then use my inverse to find my B coordinate vector of X. Being 2, 6. So to do that, my B coordinate vector of X would be the inverse times vector X, which would be 1/3, negative 1/3, 0, 1, times 6, 8. And when you multiply this, you do get 2, 6. And that shows, and that's how we would find my coordinate vector of X relative to B, or my B coordinate vector of X. Coordinate mappings allow us to introduce coordinate systems for unfamiliar vector space. So in this figure, this illustrates theorem 8. Let B be B1 to Bn be a basis for a vector space V. Then the coordinate mapping of vector X onto my coordinate vector of X relative to B is a one-to-one linear transformation from V to Rn. Isomorphism. Standard basis for P2, P1, P2, P3 equals 1 t squared. Polynomials in P2 behave like vectors in R3. Since A plus BT plus C times T squared equals AP1 plus BP P2 plus C vector P3, the b-coordinate vector of x equals a plus bt plus ct squared, which equals ABC. The vector space R3 is isomorphic to P2. And we'll talk more about that in the next example. So in example 3, parallel world of R3 to P2. Vector space in R3, this is our vector form, A, B, C. The vector space in P2, this is our vector form, A plus B, T plus C, T squared. Vector addition example, so I have negative 1, 2, 3 plus 2, 3, 5, and we know that equals 1, 5, 2. Vector addition would be negative 1 plus 2t minus 3t squared plus 2 plus 3t minus 5t squared, which would give me 1 plus 5t plus 2t squared. Informally, we say that vector space V is isomorphic to W if every vector space calculation in V is accurately reproduced in W, and vice versa. Assume that B is a basis for vector space V. Let's look at example 4. Use coordinate vectors to determine if P1, P2, P3 is a linear independent set where P1 equals 1 minus t, P2 equals 2 minus t plus t squared, and P3 equals 2t plus 3t squared. So with this, the standard basis set for P2 is B, which is 1 t and t squared. So the coordinate vector of P relative to B is the following. So we would have 1, negative 1, 0. That would be the first one. And for the second one, we would have 2, negative 1, 1. And the third one, we would have 0, 2, then 3. Then this would give us the matrix. One, negative 1, 0. 2, negative 1, 1. 0, 2, 3. And we can reduce that. The first step is I could take row 1 and add it to row 2. And get 0, 1, 2. Then I can take negative row 2 and add it to row 3. And notice I have 1s down the main diagonal. So by the invertible matrix theorem, the coordinate vector of P relative to beta for 1, 2, and 3 is linearly independent. and therefore P1, P2, P3 is linearly independent. Coordinate vectors also allow us to associate vector spaces with subspaces of other vector spaces. So looking at example 5, let B equal B1 and B2, where B1 is 3, 3, 1, B2 is 0, 1, 3, and let H equal the span B1, B2. Find the coordinate vector of x relative to B if x equals 9, 13, and 15. So first we're going to let C1, B1 plus C2, B2 equal x. So we would have C1 times 3, 3, 1 plus C2 times 0, 1, 3 equal 9, 13, 15. So we're going to have our corresponding matrix. And we're going to row reduce this until we get an answer. So the first thing I'm going to do is take 1/3 of row 1 to get 1, 0, 3. The next step, I'm going to take -3 of row 1 and add it to row 2. And that would give me 0, 1, 4. So the next step, I'm going to take negative row 1 and add it to row 3. And that would give me 0, 3, 12. And then I'm going to take -3 row 2 and add it to row 3. And right here, we would have our answer. So therefore, C1 equals 3 and C2 equals 4. So the coordinate vector of x relative to B is 3, 4. And 9, 13, 15 is in R3 and associated with vector 3, 4 in R2. It is isomorphic to R2.